Hello, thank you for having me here. I'm just going to make a very quick poll. How many of you, just raise your hand, are familiar with optical flow algorithms? And how many of you have an interest in optical flows, regardless of being experienced? Okay, very good. Thank you. So yes, I'm a NASA postdoctoral program fellow. I started that 2 years ago, and I specialized into astrophysics, and more specifically into solar physics. I study the sun. I study the sources of solar flares and solar eruptions by tracking the flow fields at the source of these events. Why do we do that? We do that to understand the physics of our nearest star, the sun. And we try to understand how does the hot gas, called the plasma, circulate on its surface. We want to know how it interacts with the solar magnetic field. And finally, how are solar flares and eruptions triggered? Can we predict them? Or more generally, can we hear them in a distance? So I will go back to the basics, introducing you to what is the surface of the sun, what it's made of. And then I'll go into more details into the algorithms for tracking the flows at the solar surface. I will also give some details about algorithms to track the magnetic flux on the sun. And then there will be a little case study to look for triggers and precursors of solar flares. So the surface of the sun, the one you actually see by eye, is called the photosphere. And temperature is about 5,700 degrees. It's very thin compared to the size of the sun. It's just 100 kilometers. It's composed of mostly hydrogen and helium. So what you're looking at is an image taken from the Solar Dynamics Observatory, SDO, through an instrument called HMI. And it's in grayscale because the detectors are monochromatic. So it's very arbitrary now how I present it. I chose grayscale. The Earth is on scale for if you don't really know what's the size of the sun. And let's look into more detail. When you look closer, you start seeing a sort of granular pattern. And when you look really close, you actually see what we call the granulation. And so these images are very high resolution. And so they are 4K by 4K images, and the instrument is sending those images to us with a cadence of 45 seconds, 24/7. There's another instrument called AIA. It takes images of the corona. I will show that later. But basically, these two instruments per day send us 1.5 terabytes of data. So when you look at this dynamically, and here is an image series from another satellite who takes even more at high resolution, but with a smaller field of view, this is what the sun looks like, what the photosphere looks like, granules. These granules, they move, grow, shrink, can explode, and there's also an oscillation pattern. I'll talk about that later. The size of the granules is typically 1 megameter, 1,000 kilometers, and their lifetime is about 5 to 10 minutes. That means that after 5 to 10 minutes, this whole carpet of bumps is completely renewed. And tracking plasma at the solar surface basically relies on tracking the motions of these granules. One of the very first technique to track granules was to use the so-called local correlation tracking method. The local correlation tracking consists in calculating a number, the local correlation, to give you a number of describing how much two areas in consecutive images look alike. And so the local displacement of the feature, for example here to go from J to K, would be the one for which that metric is maximum. And again, that metric is called the correlation. But the problem is, as I said, it's a number that tells you by how much two areas in consecutive images look alike. But on that, granules, they already look quite self-similar. And that is actually enough to fool this algorithm. And so you end up with outliers, because in those, little areas in which they look for those displacements, they can find twins. You know, another granules that is completely unrelated to the other one. It doesn't move there, but it looks enough the other one. And so that's how you get outliers. So this is a motion that is not physical. It is just because of a similarity metric which is not robust enough. And so that makes this algorithm a little bit flawed for this application. But don't get me wrong, for other cases this is good. If you know about correlation tracking, it is just the nature of the data that makes correlation tracking not so well adapted. So I've worked during my PhD some years ago on another tracking technique called ball tracking. So I'm not the original author of that, but I have developed that and made it even better for this kind of application. It is called ball tracking. And so the purpose of ball tracking is to track granules much more accurately than local correlation tracking. The principle is to throw balls between the granules, and with an equation of motion, they would settle into the local minima. And as the granules move, grow, shrink, they push the balls around, as illustrated in this video, which is not this is not synthetic data. This is actual real data. The carpet that's moving with the bumps is actually directly taken from those data that you have in the background. And how do we get the flow? How do we get the flows? We differentiate the final positions of these balls to get a flow field. I will show you in more detail how we do that. First, to be able to track the granules with those balls, we have to rescale the data, because these 2D images they are maps of intensity, and so they have their ranges from thousands of over thousands of data numbers. We need to rescale that so that from top to bottom we have an intensity that ranges much more, which is more friendly, so that the balls could settle into these local minima. And once you do that using simply mean normalization, so you subtract by the mean and you divide by the standard deviation, you obtain an intensity map that, when you look at it in 3D, looks like this carpet full of bumps. And the initialization of such algorithm is very simple. We just have a regular grid, so just a mesh grid that initiated, so that you have an equal spacing between the balls at the beginning. And there is a rule to put the balls on the surface, and they basically, the penetration of the data surface into the ball is about 10% of the radius of the ball. So here is an illustration of the principle of ball tracking. So each ball is animated by an equation of motion. The forces are some sort of a restoring force that is a function of the penetration distance of the data surface into the ball. So the more surface is into the ball, the more it pushes it. If it's asymmetric, the ball will move. And that's how they end up settling down into the local minima. Gravity makes gravity, which is completely unrelated to the sun's gravity, it's a numerical one, is just here to keep the ball down on the surface. Finally, and most importantly, there is damping. The damping here is proportional to the velocity, and it is to control the inertia of the ball and gives us some degrees of freedom on how tolerant we want to be with noise. And with this equation, at each image we integrate this equation of motion. They settle down in the local minima. And then the next image comes in. The granules have moved it has moved a little bit, and we go again with that equation, and it continues following these local minima. Beware that we are interested not in the velocity of the ball in that equation. We are actually interested in the final positions of the ball, and the velocity we're looking for is the one you get from differentiating the final positions of the balls. Here is an illustration of how one ball behaves with this, in this carpet full of bumps. And more importantly is that we're going to throw a lot of balls on the surface. We want to sample the whole map. And so there are going to be thousands of balls. And so for the algorithm to be efficient, it has to be best if it can be vectorized. That means to exploit the fact that the equation of motion is independent from one ball to the next. And having a vectorized code makes it much more flexible if you want to accelerate it using, for example, GPU computing. So you can see in this code snippet, there is not a single for loop to compute the forces and the motion of all the thousands of balls on the data surface. So that makes it very, very quick if you are bound to using, say, Python on a desktop computer. So to give you an example, 1 week of data, which can be about 1 terabyte, actually. It takes about a few hours to compute with only one CPU. Remember, we're talking about high-res images every 45 seconds over 1 week, while local correlation tracking would take many, many weeks to process that with a lower quality. All right, so this is what the motion, the tracks of the balls look like when you do not filter or average that. It looks like a very stochastic motion. That means like some sort of a random walk, and it's hard to make sense of that because what you're looking at here is simply the intrinsic motions of the granules. But again, when we do solar physics, and in my case, I am not interested in the motion of the granules per se. I am interested in the drivers underneath that are moving all these granules around, because this is what controls the magnetic field. And when you average these displacements and you divide by time, then you get the actual velocity field. And if you average that over time and over space, this is what you get. And to put in the context of the images, remember that we track granules, but what we derived are the flow fields who seem to have a pattern that goes beyond the characteristic size of the granules. And this is invisible to the naked eye, but this is a real physical structure that we call the supergranules. The supergranules are these superconvective flow cells that are bigger than the size of Earth. So to get there, it's not just about applying this algorithm to the images. Many, many problems had to be solved. Everything is done in Python. The first step is to filter the images. When you look at that, you can see that the granules, they are not homogeneously, the intensity of the granules is not homogeneous, and you can see some sort of an oscillation pattern. It's like it flickers. And you can filter that with Fourier, but if you want to filter pure granulation signal, you need to basically sort of guess what is a spatial scale you want to select so that you can get rid of the lower frequency oscillations in the Fourier space domain. But where do you stop? How do you select these scales? And so during my PhD, I did some random guess until it looked nice, but that was very qualitative. And so more recently at NASA, with other experts in image processing, they told me, hey, you could use something called the structural similarity index. And so that's one example how to know that you can stop, well, how you can best select the scales that you want to track. So in this example, you use that by you filter the different images until the structural similarity index becomes constant. And so basically I stopped about there. And so that even if you filter even further, you don't gain anything. And so that's when you know that you can stop. And you don't want to go too far, because then you start cutting down into the granule signal, and you want to keep those granules intact. So this is on the left the unfiltered images, and on the right the filtered images, where you have a much more pure granule signal. So when you track that, you know that you are actually tracking those granules and not something at lower frequency. Again, I'm talking about K-space, Fourier space, converting space to frequencies and not time to frequency. Next. There. All right. Another, something else to solve was the missing bin problem. So the balls are to settle in the local minimum. But that means that if you have plenty of granules, they would end up converging to the same local minimum. And so you would lose balls on the maxima, because they fall from there, they converge to these local minima, and at some point then you're actually missing some stuff. So how do you solve that? On the left, I've plotted the what happens when you, after the integration of the balls, and you have all these empty bins. And so these are the bins that where you will not be able to tell what the velocity is. And originally, the original author tried to solve this by simply throwing more balls where they were where you had empty bins, but still, you still had at the bottom lots of empty bins, so that was not enough. So for that, you need to enforce continuity by relocating the balls in overpopulated bins into the depleted bins while maintaining uniform density and a constant number of balls. So in physics, we call that continuity or conservation of mass. Whoops. Another something else to improve was to have a finer sampling. For this, if you remember, I was saying that with the images of the granules, I track the local minimum. A local minima would be in those dark area. They are the intergranular lanes, so the space that separate the granules. But still, when you do that, you are bound to have the balls settle there and always leave, no matter what, the centroid of the granules because they are at higher height. So by inverting simply the image, the local maxima becomes local minima. And so you just track both at the same time, and in the end, you average all that, and you get a finer sampling. Now, how do you get a sense of the quality of the tracking? How do you get a sense of how good you are doing in the tracking? Because again, there are plenty of things you can't really see and check by the naked eye. One way to do this is to simply impose a drift on the data. So if you look carefully on the top and bottom, so on the left is the filtered one, the left is the original one, the right the filtered one. They sort of shear with respect to each other. And so these image series have simply a drift at a given velocity. And I've used like 10 different velocity drifts. I make those series of images drift at these known drift velocities so that I can track each of them. I look at the average velocity and I plot for the top side tracking and the bottom side tracking. I plot these curves. Unfortunately, the response is linear, but it is not a coefficient it is not a correction factor of 1. It is something like 1.3, 1.4, because the balls take some time to settle on the local minima, and we don't necessarily need to wait that they really reach there. On average, that's enough to make them settle, say, halfway through, because the next image, anyway, they will be touching the other granules, going to push them in another direction. So you don't really know to settle down in the local minima. And so that makes it more efficient, because you don't need to have so many integration steps to make them settle down the local minima, as long as you perform this calibration and get those calibration factor, of course. All right. So another qualitative assessment of the accuracy, and I'd like to stress a point there, which is it's more an anecdote. I talked about precision of the algorithm, and I'm talking about accuracy, and what's the difference between there? And I'm not a native English speaker. I'm actually from France, and funny thing is that in French, when you translate precision and accuracy, you get the same word. It's called précision. Same word. And it took me a while to understand that when I was reading physics books. And so the difference is very, I like to compare that with a simple experiment. Imagine that I give a ruler to every one of you, but I'm giving you a ruler that I've made myself. And I ask you to measure something, say, I don't know, the size of the chip of your phone, a nano SIM, whatever, and you give me the numbers. And you're gonna oscillate a little bit around the true value. But is that the true value? How do I know the true value? And how do we know that the ruler you have is good? So you can make a very precise measurement with that ruler because you have very good eyesight. And so you make a very precise measurement. But if you have a very bad eyesight, you're going to have something not so good because it's going to be blur, and you're going to give me a different number. And then I'm going to take an average, and I'm going to take the standard deviation, and that is a measurement of precision. The accuracy is how accurate is my ruler. That ruler has been built, and it's been, many, many times ago. The reference for the meter was in Paris, called the étalon mètre, and that's how people were calibrating their ruler to get the meter. But you have to rely that it's actually correct to make sure you have an accurate measurement. So on the sun, it's even more important because you can't check anything by eye. And so in that example, I've shown you how I check the accuracy by having an independent data set, which is in the background the magnetic field. The magnetic field is a different data set, and we know that the boundaries of the supergranules are expected to concentrate the magnetic flux. And if you plot the boundaries of the supergranules that you get from the velocity flow field, and I'll show you later how we do that, you have a qualitative assessment of the accuracy. So if you have these lanes that corresponds to where the magnetic flux is meant to converge, if they do not line up with the high concentration of flux, for example here, see at the top, if they don't line up with that, you may have made a mistake. All right? Another way to compare is to use simulation. So these are quiver plots. I've shown one earlier. Quiver plots is simply a plot where you have arrows at each velocity grid point. And on the left, it's a simulation, physics simulation of the granulation that has been, for which we just took the velocity flow field, compared it to velocity and compared with ball tracking. So the true value of the velocity lies in the MEM-HD simulation. You compare that with LCT, local gradient tracking, and ball tracking. And for example, you can see that LCT has trouble resolving the fine structure of the flow patterns. And ball tracking is qualitatively doing a slightly better job. And finally, another way to optimize, back to the precision, is to use the discrepancies between the top side tracking and the bottom side tracking. And by minimizing this discrepancy into the input space, so the parameter space that controls the geometry of the ball, the physics of this model where the ball settles into the local minima, you can actually get a set of ideal parameters, but it is quite robust. You can see, for example, here, that is the characteristic penetration depth. It's characteristic to the dynamics of the ball. You can take some values, but you do not actually change much the precision, and that's because there is this calibration process that makes sure that you've done the job right. All right, so how do we visualize these large-scale patterns of 2D flow fields in Python? So one example, quiver plot, map of plenty of arrows, gives you some pattern. It's nice, but it's not great because it's very difficult to work with components of vector fields. Another way is to look at streamlines, but again, it is a visual aid. A streamline is a line that is always tangential to the velocity vector. And the background is the speed, the magnitude of the velocity. So that's another way to have a scalar map of the pattern of the flow. So you can see that in the blue, you are halfway between the center of the supergranule and the boundary of the supergranule, where again, the horizontal velocity is minimum. But we know from other measurements that this is also where you have downflow. So where it's minimum, it's actually a downflow. So it's sinking down into the sun. Another way to have patterns in the flow map is to use derivatives. It is actually the thing you should not do. It's very blur, and people are very frustrated with that. And so we have to do better. So one way to do better is to use a convection cell recognition algorithm, where you simply reverse the velocity and you integrate the trajectories of that reverse velocity. And by doing a distance transform of that, so that means putting the final distance and mapping it to the initial positions, you end up with these sort of maps where you have a lane, where you have convergence of flows. And it's very, very useful. And the result of this map is the one at the bottom right, and it comes from that flow field there. So it is much more cleaner, much more easier to work with. You can exploit that for data mining. You can do some segmentation to calculate the area of the supergranules, track their centroid, and this way you have a good data set for tracking the evolution of the sun over the solar cycle. All right, next algorithm is, how do we track the magnetic flux? Well, I still use the ball tracking paradigm, but on different data. So those are so-called magnetograms. They map the photospheric cut of the magnetic field, more precisely the line of sight magnetic field. So that is one component of the magnetic field vector. Plus is white is positive, black is negative, and these are both polarities of the magnetic field. And by rescaling that, you can also obtain a sort of carpet full of holes. But unlike granules, these are non-homogeneously distributed. And so that's an added problem to this optical flow tracking problem. So with a slightly different code, you can still track that in a non-homogeneous grid. So you track the magnetic elements wherever you have one. With granules, it was easy because you had granules everywhere. So you can put balls anywhere and they would track. But here it's not the case. Nonetheless, thanks to the ball tracking paradigm, you can track efficiently and also have the univocal labeling of the moving magnetic features. And so that's a very difficult problem for many image processing problems trying to match and track features. So this labeling problem is that when you have two features, you think you track them, you can get a velocity, but when you have many, it's difficult to keep track and to label them independently. And especially for having a unique identity, a unique label for each other. For example, in this problem, you can see that many of the magnetic elements emerge, or they cluster out. So when you track one element, then cluster out, how do you do? Because you had only one tracker at the beginning. And so with magnetic ball tracking, it's very easy, because as soon as it detects a new feature, you're going to drop a ball on there with a new label. And so you get a history and a tracking of each independent magnetic fragments wherever they come from, whenever they rose, whenever they die. Well, don't die, they just disappear. All right, so moving up to active regions, you're looking at the application of magnetic ball tracking with an emerging active regions. Active regions are what are giving you sunspots. So this is a region of very intense, very high magnetic field. And magnetic ball tracking can automate the process of detecting them and tracking them. In this example, this is another way of looking at the time series of the result of magnetic ball tracking. So on the left, you have all the magnetic elements that are tracked. On the middle, it's a segmentation of the tracked fragment. And on the right is a visual aid to check the tracking. So when you have, it's called, I think it's called color component labeling. So if you have a magnetic fragment who doesn't change color over time, that means you tracked it properly, because it's always associated the same label. That label is the same as the numbers that you saw earlier, except there it's coded in a color table. So it grabs the color in the color table. If it doesn't change color, you're good, you tracked it. If a single fragment over time changes color, means you're wrong. Tracking failed. All right. Now I'd like to dive deeper into a case study of analyzing solar eruptions. So here I've plotted an eruption of a so-called filament eruption observed with another instrument, the AIA instrument. Same satellite, but looking at a different layer of the atmosphere, a hotter layer called the corona. And ooh, it stopped. There. And here I've combined three different layers associated them to RGB, and so this is an artificially colored image. You wouldn't see that by eye. Temperature is millions of degrees there, compared to the photosphere, who was just a few thousand degrees. And the case study is an X-class flare, so a very big flare that happened last year. And you can see it here. It actually is very bright, and it's erupting. So lots of energy that were directed toward Earth. So it's called a flare. And at the base of the flare, you've got these little thingy there. These are sunspots. And this is where the magnetic field loops that are very hot, they emanate from these sunspots. And so here is a case study of that sunspot earlier in time, where it was still near the disk center. It was looking like this sort of, call that a flux rope, plenty of loops. And with the different tools that I showed you, the tracking of the flow fields, detected precursor phenomena 10 days prior the eruption. So on the left, you see the flow fields where I plotted the streamlines coming out of the sunspot. The blue lanes on the left and on the right are the result of this algorithm applied on the flow fields to get the boundaries of these supergranules. And around the sunspot, you have also these boundaries. So on the right, you see the background. It is a magnetic field, again, plus, minus, opposite polarities. And you can see emergence, very strong emergence of magnetic flux. And this is the source of the energy that is later released in the solar flare. The point of the algorithms is to study the flows that are the evolution of the flows around the sunspot. And using these series, using the framework, the tracking framework, we could analyze and detect that before the emergence of magnetic flux, there is a disruption of the pattern of the flow fields that are plotted here with both the boundaries of the flows and the streamlines of the flows with their quiver plots, with the arrows. And you can see that it's sort of escaping away from the sunspot, whose center is around there. And later on, you have the emergence of magnetic flux. The magnetic flux starts to emerge at that point there. So with these algorithms, we can detect the emergence of magnetic flux several hours before it happens. And so this is an example, another example where you have here the boundaries of the flows around the sunspot are quiet. And there, down there, you see a bulge, and here a stronger bulge. And that is precursing the emergence of magnetic flux in black and white. So to summarize, so I've shown you here examples written in Python of application of optical flow tracking algorithms for analyzing the solar plasma from real observations. And they provide us new descriptors of the solar activity. For example, the boundaries of supergranular flows and the flows around the sunspot, which is called a mode flow. We can analyze the properties of the magnetic field through accurate tracking, labeling, and segmentation of magnetic elements that peer through and flow over the photosphere. So that calls lots of different background, computer vision, because there is segmentation there, physics, because you need to implement physics-aware algorithms. And so these descriptors are meant to become input to machine learning and deep learning for assessing the ability to forecast flares through statistical analysis. So if you're experienced in solar flows, in optical flows in general, and you want to try tracking SDO data and solar flows with your own algorithm, please feel free to do so. The data are fully available. My tracking framework, if you want to try that with other data, or want to play with that, improve that, if you have nothing else to do, it's available freely. It's on Bitbucket. And if you have questions, you can contact me. I'm on LinkedIn. Email me at NASA. Be really happy to discuss all that. Thank you very much for your attention. Yep. No, it's not. So it's I was talking the inner loop. There is no inner loop, but there is the outer loop. It loops over the images. Yes, it's the only loop that there is. No, if you figured out a way to eliminate that. No, I haven't. That would be great. Yeah, it's fast enough though. This way. Well, I mentioned the benchmark on one CPU, but in fact, typically use 4 CPU. The 4 CPUs are meant to, for example, track the top side tracking and the bottom side tracking. These are parallel. I mean, they can be, it's parallelized, and so that makes it even faster. But yeah, that would be great to have the time also vectorized.
What's the maximum surface area you would vectorize this algorithm on?
The maximum what?
The sun surface area.
Okay, so we're limited by projection effects. So in terms of image size, the maximum I can do at a time would be 1K by 1K. Because then, beyond that, the granules undergo projection effects, and so you're losing resolution because you're looking at them on the side, and so one pixel doesn't have the same physical scale as in the disk center. And so the maximum is 1K by 1K, so that's, you know, the full sun would be nearly 4K by 4K, so that's like 1/8 in surface, 1/16. Yeah. 1/16. What's that? Yeah. Yes, and we don't have them, unfortunately.
So with the ball model, the restorative force, did that include balls passing through each other? Or
Yeah.
were they allowed to pass through?
So yeah, because the point is not to model billiard. So no, they do not collide. They go through. Yeah. There is one point I didn't mention because it was a bit too technical, is that to be able to repopulate the empty bins, there needs to be some internal communication between the balls to know where each other are. But fortunately, I also vectorized that. So it's also very, very fast. So using this sort of coarse grid thing in which you have this bigger grid cell and you check that you make sure you have at any time one ball in each of those cells. That's how I relocate them.
So they pass through the same cell?
They pass.
Different velocities.
Yeah, because they can come from different points. And so they can come from opposite velocity, opposite directions. But once they settle down in the same, they will stay at the same positions, right? And at that point, then, I only keep one ball tracking that place. And the other balls that I've converged there, they are the very ones that are relocated elsewhere to continue tracking on the depleted bins.
Thank you.
What packages did you use to create the visualizations in this presentation?
OK, to be fair, there are some of what you saw was from my historical research. It was in MATLAB. The more recent one, like for example this one there, it's with Maya VI.
I'm sorry?
The one you see right now, like for the flows, it's with Maya VI. I have a problem with the streamlines. So you see those colored lines, that's called the streamlines. I have a problem with Matplotlib implementation of streamlines. I can tell you there is actually not a bug, but a mistake, a physics mistake. And so when you plot streamlines in Matplotlib, well, I actually disrecommend you to do so. There is something wrong there. And so that's why I had to use another package in Matplotlib. It's a problem for me, because the Maya VI is a 3D visualization software. I'm using it for 2D projections. It's highly inefficient for that. And I have to play around with the camera. I don't like that because I'm using purely 2D data. Your other question was for other visualizations. So the other plots that you saw was done with Matplotlib. For the videos that you saw, just the quiver plot with arrows, that was also with Matplotlib.
Have you considered not doing this in 2D, but you actually doing ball tracking on the sphere itself?
I tried that. It is theoretically possible, right? But then you can't have a constant size of the balls, because you need to compensate for the change of the ellipse of transformation due to projection effects. Because if you have a constant size of balls to track a feature that has a constant size on average, you're losing resolution, and so it wouldn't compensate for that. So when I tried that, it was completely wrong, and so I need to remap, and yeah, I can't do it on a sphere.
So you were talking about forecasting the sun flare, right? Can you even forecast the extent of the sun flare? Like, is there any
Extend what?
extent of the sun flare, like how big the sun flare would be?
So yeah, that's actually where things come into play. I'm not trying to predict whether it's going to flare or not. Yes, this whole thing, it is to quantify the energy that could be released should it flare. If it flares, how much energy should I expect? Because by tracking the flows, you have a vantage point on the kinetic energy that gets converted into magnetic stress. And this is what accumulates energy before a flare. Yeah. We have to continue later.
Yeah, thank you.